Hey everyone, another day, another DSA problem. So today we're going to look at 3499, maximize active section with trade 1. Okay, so let's look at the problem. This was yesterday's daily problem. I didn't get time to make a video yesterday, so I'm doing it today. All right, so it says you're given a binary string S of length n, where 1 represents an active section and 0 represents an inactive section. So you have to perform at most one trade to maximize the number of active sections in S. Okay, and they've given the definition of what a trade is, and they've given another condition of kind of peripheral ones that have to be added. So I'm going to go ahead and show this on my iPad so we can better understand this, okay? So what's given? A binary string S consisting of ones and zeros, all right? So 1 means active, 1 means active, and then 0 means inactive, all right? So the goal is to perform at most one trade to maximize the number of ones in this string, okay? So the question is, what is a trade? So they stated, and the problem is the same thing. So a trade is when you convert a contiguous block of ones that's surrounded by zeros into all zeros. And then in the next step, you're going to take a contiguous block of zeros that's surrounded by ones, and then you're going to convert that to all ones. And eventually, the goal after doing this trade is that you want to maximize the number of ones in your string S, okay? So let's check an example over here to see what a trade is, right? So they've also mentioned to us that by default, whatever string you're given, like in the 0, 1, 0, 0, you have to consider that at the end, there is 1 here and 1 here, but those ones will never contribute to our final answer of active ones, okay? So let's check the first step of the trade. I'm going to take this one because there's only one block of ones, right? And convert it to a 0. So now we have 0, 0, 0, 0, okay? And then we have ones to the side. Then we do the second part. We have a contiguous block of just zeros, which is surrounded by ones. By default, the ones are there. We're going to convert this to all ones. 1, 1, 1, 1. Okay? And now our active blocks went from being just 1 to a count of 4 active blocks. Active blocks is just the count of ones which are present in the string. Okay? So, it's worth making some observations to understand what the solution of this problem actually is, all right? So let's check this over here. We'll consider our peripheral, like these ending ones over here by default to make things easier. Then we're gonna go to our first step. Our first step is to take a contiguous block of ones and then convert that to zeros, all right? So I'm gonna look at my contiguous blocks. I have one over here. So let's say I'm gonna convert that, okay? So I'm going to convert that to zeros, all right? So I'll make that 0, 0. Okay, so let's just write these ones everywhere so it's better. All right, so what happens after I do that? 0, 0. And now I look at what my string has become. It's 0, 0, the 0, 0, another 0, and then back to this 1, 0, 0, 1. Okay, so let's check here as well. What was our initial count of active blocks? Okay, so initial active was, so we have 1, 1, 1, 1. Okay, so we have 4 active ones, all right? Okay, so the first step has been done. We have converted our contiguous block of 1 surrounded by zeros to all zeros. Now we're going to do our second step, okay? So again, we have 1 here, 1 here. And our second step says that we have to take a contiguous block of just zeros, which are surrounded by ones, and we have to convert that to all ones, okay? And now I see my goal is to maximize the number of ones, right? So I'm going to look at the largest block of zeros, which is this, okay? So I see 5 zeros. Now I'm going to go and convert all of them to ones, which is our second step, right? So if I do that, 4, 5, and then that 1, which is already present, then we have 0, 0, and we have 1. Okay, so now let's look at this. So how many active blocks do we have? So our final active is, so we have 1, 2, 3, 4, 5, 6, 7. Okay, so it's 7. Now, I want you guys to observe something. So they first tell us to take ones, convert them to zeros, then convert them back to ones because we're taking that whole block of zeros now, right? This or any other block. But those ones just get converted back to ones, right? So that's something which is worth noting because if you look at this area right here, right? So this is where that happened, okay? So these ones just converted to zeros, but they converted back to ones. So to our final answer, they don't contribute anything extra because their contribution was already included for in this. So what is actually adding up? All right. So let's look at this. Let's see this. Look at this and then look at this. Okay. So those were the zeros which got converted to ones, which are an additional addition, like an additional increment of ones to our final active ones, right? So if I look at that, there's 1 0, 1 0, 1 0, which is 3 zeros. And I saw that I already had 4 ones. And these 3 zeros eventually converted to ones, right? So if I do 4 plus 3, what does that give me? It gives me 7. So what does this mean? So this part over here, let's consider this like A. And this part over here, let's consider this as B. So our total gain is actually defined by the sum of the surrounding contiguous zeros, right? Like the length of the surrounding contiguous zeros. So the gain here actually becomes A plus B. And ones don't matter at all. It's just that we're trying to maximize the surrounding zeros that can add up to this, okay? So that's what I've written over here. The goal becomes we have to find the maximum sum of adjacent zero blocks. All right, so we were able to take this problem and narrow it down to something which is achievable. So this is the algorithm we're going to follow. First thing is what I did. I'm going to count the initial number of ones, okay? Then I want to find the lengths of all the consecutive zero blocks, all right? So this can be just another pass. I'm going to note those and keep them maybe in like an array, okay? And then I'm going to do another pass where I'm going to check these consecutive blocks, right? These adjacent blocks of zeros. Let's say the first one was size A, the second one was size B. Now I'm going to try to maximize A plus B going across all of these pairs, all right? And then I'm going to take the maximum gain, which is basically what I mentioned, the maximum of A plus B, that value. And eventually I will return the number of ones I already had and the number of zeros that just contributed to my active ones, right? So original ones plus maximum gain. Now, there could be an edge case, right? So there could be a case where there are no like two groups of zeros. Okay, let's look at this example here. If you see this, even if we convert, so we can never convert it actually. So this becomes, even if we consider there is a 1 to this side and a 1 to this side, and we have 0, 0, 0, 1, 1. So these ones can never be converted to 0 because they have to be surrounded by zeros. But look what they're surrounded by. It's a 1 and a 0. So we see that if there is ever a case where there are fewer than two, if there are fewer than 2 zero blocks, then we have no valid trade. There's nothing that can be done. And we're just going to return the number of active blocks we initially had. So we're just going to return 2 in this case. Okay. So let's analyze the complexity over here. So what were we doing? So we're going to find this one's count. Okay, this is O of n. And the length of all consecutive zero blocks. Again, this is one pass O of n. Then we're going to go ahead and compare pairs O of n. Okay, and then we just take the maximum of all of that. That part doesn't add up. So this is O of 3, O of 3n, which is O of n. So our time complexity is O of n. And then we're actually holding those zero blocks, right? So let's consider that n O of n. Okay, so this is the complexity analysis. I hope you guys understood the solution. I'm just going to code it up because people have asked me to. So let's just go ahead and check the code. Okay, so first thing I want to do, I want to check the size of S because that's always the best thing to do. And then we were talking about counting the number of ones, right? So let's just do this as count one is equal to s dot count of one, because it's a string. Okay, we did that, and then we want to check our zero blocks, right? So let's go ahead and create something like zero blocks, and we'll go ahead and start appending to it. So what I'm going to do is keep a pointer starting from the beginning. Then I'm going to go as long as I have zeros, and I'm going to try to figure out the length. All right, so we can do that like this. We'll start I is equal to 0 while I is less than n. Let's keep a starting pointer. So start is equal to I. And I want to keep continuing as long as we have the same contiguous number pattern, right? Contiguous string subsequence. Sorry, substring. Anyway, so what will I do? While I less than n. Okay. And s of I is equal to s of start. What do I want to do? I want to do I plus is equal to 1. Okay. So eventually, once it comes out of this, then that means s of I is not equal to s of start. So it has gone to some other element, either 0 or 1. So that means that I now have a contiguous length, right? And this the off by 1 error is taken place, it's taken care of because I've started from 0 and I've gone to the next element. So that's there. So I'm just going to do a check to see if start was actually the starting element was 0, because I only want to consider those. So if s of start is equal to 0, then I'm going to do 0 blocks dot append. What was the size of this? So it would be I minus whatever start was. Okay. Yeah. All right. So again, for the next iteration, start will go to whatever the next I was, and we're going to start considering that. So now we want to do that pairwise comparison within 0 blocks, right? So let's go ahead and get the length of zero blocks. We're going to do our check to see if m is less than 2. If it is, then I want to go and return my initial count of zeros because there's no valid trade. So I'm going to do return count of 1, or else we're going to go ahead and check it, right? So let's keep this next value as count of 2 is equal to 0. And then I'll do for I and range m. So we want to, no, not m, actually. We want to do a comparison with the next element, right? So this is going to be m minus 1, okay? So we're going to do count of 2 is equal to max of count of 2. And the sum of like A and B, those consecutive 0 blocks, right? So it's going to be 0 blocks. Okay, it's going to be 0 blocks of I plus 0 blocks of I plus 1. All right. So by the end of that, we would be getting like the maximum value of what that's supposed to be. Yeah. And then all we have to do is return count of 1 plus count of 2. Oh, okay. I just want to make sure I didn't make any typos or any mistakes here. Okay, this should be fine. I hope so. And yes, it does run. So let's just write the time complexity. That was O of n. And then our space complexity was also O of n. So yeah, that is the solution for this problem. And today there is a second version of it, which is based on segment trees, which is a lot more complicated. I will probably try to make a video for that. But anyway, I hope you guys understood this. And yeah, happy coding, everyone.